Hello everyone, my name is Keren Zhou. Currently, I am a graduate student at Rice University. Today, I'm going to talk about our tool, ValueExpert, which is a tool that explores value patterns in GPU-accelerated applications. Nowadays, GPUs have been extensively employed for acceleration in HPC and deep learning domains. Moreover, hardware vendors, including Intel, NVIDIA, and AMD, have devoted significant effort to develop the next generation GPUs. Since all of these important applications have adopted GPUs for acceleration, it is also important for us to tune application code to better harness the full power of GPUs. To better assist performance tuning, we use GPU performance tools. Traditional and popular tools, including NVIDIA On-Site Systems, On-Site Compute, HPC Toolkit, and Tau, focus on hotspot analysis. These GPU performance tools profile executions and dumps a profile that shows how much time has been spent on each GPU API or GPU kernel. So below is an example profile from On-Site Compute. From the profile, we can see the number of cores, the total duration, and average duration associated with each GPU API, so that we only focus on the hotspot GPU APIs. However, these tools lack one important analysis. They don't associate hotspots with their root causes. To further demonstrate the problem, here's a motivating example from PyTorch. In this code snippet, there is a replication pet3d backward CUDA function. At the beginning of the function, we initialize a grid input array using A10 zeros like. This function is going to initialize an array and then set all the elements on the array as zeros. Then we call another function backward out CUDA template. In this function, again, we set the grid input array with zeros. Since there's actually no operation on grid input array in between, we see these two updates with zeros are redundant value updates on the grid input array. By eliminating the zeros like function invocation and replace it with a empty like function invocation, we can remove the filling operations with zeros. So this single optimization improves the operator by 1.08x on our NVIDIA A100 GPU, and this optimization has been upstreamed to PyTorch repository. To address problems like this, we developed a ValueExpert. So compared with traditional GPU performance tools, ValueExpert shifts the focuses on hot GPU kernels and hot memory movement to redundant and useless computation and unnecessary data movement. The core features of ValueExpert is value pattern analysis, which consists of both microscopic value patterns and global value flows. Microscopic value patterns analyzes value access within each GPU kernel, and global value flows track value changes across GPU APIs to enable optimization. ValueExpert is applicable, efficient, and insightful because it can be applied on a wide range of benchmarks and applications with acceptable overhead and useful insights. ValueExpert categorizes many value patterns. On the high level, we divide value patterns into coarse-grained value patterns and fine-grained value patterns. Coarse-grained value patterns happen at each GPU operation. Fine-grained value patterns analyze value accesses within each GPU kernel. For fine-grained value patterns, we further divide it into redundant values and duplicate values. Redundant values analyze value changes before and after GPU kernel. Duplicate values analyze if GPU operations involve the same values. There are several fine-grained value patterns, including frequent values, structured values, and heavy type. Also, there's one special kind of fine-grained value pattern, approximate values, which round up floating point numbers and cast it to other value patterns. In the following few slides, we're going to show detailed examples of redundant values, frequent values, and heavy type. Let's begin with the redundant values, which compares values of data objects before and after GPU kernel. So we intercept memory allocation APIs to track memory allocation so that we can identify different data objects. Then at each GPU kernel, we record values before and after GPU kernel invocation. In the example below, before the invocation of GPU kernel K1, we identify the range of object A and object B. Then we copy values that have been updated by GPU kernel K1 after it's done. Again, we identify the regions of A and B. Then we compare the values before and after the invocation and found that 66.7% of A remain unchanged after the invocation and 44.4% of B remain unchanged after the invocation of kernel K1. Next, we're going to talk about two fine-grained value patterns. The first one is frequent values, which indicate values are accessed more frequently than others. At runtime, we instrument GPU memory access instructions and record the values accessed at each address. So in this example, we collect all the values accessed and then count a value distribution. We found that value 1 has been accessed 6 times, which takes 66.7% of all the accessed values, which is greater than 50%. So it's accessed very frequently comparing to other values. Again, using the same value distribution, we found another problem. All the values we accessed are within the range of integer 8. So it could be represented by integer 8 if it was previously represented by integer 32 or floating point numbers. In this way, we can reduce memory transaction cost. So this value pattern is categorized as heavy type, which means values can be represented by narrowed data types. By applying ValueExpert on 10 benchmarks and 9 applications, we found that the 8 value patterns we categorize can be commonly found in these applications and benchmarks, which demonstrate the fact that value patterns are pervasive and important in GPU-accelerated applications. So after analyzing value patterns, in the next, we are going to talk about a special profile called value flow graph, which facilitate value pattern analysis and enable optimizations. At the first, I'm going to show you how we can construct a value flow graph from an example program shown in the left side. So on the right side, I'm going to use the line number of each GPU operation as its node number. At the beginning, we allocate an array A on the device. So we create a node 1 to represent operation 1 that allocates A. Similarly, we create another node 2 to represent the allocation of array B. Then at line 3, we use memset to set all the elements on array A as zeros. Since array A was first allocated by operation 1, we insert an edge that represents a write dependency between operation 1 and operation 3. Similarly, we insert another edge between operation 2 and operation 4. In the next, we launch a GPU kernel that sets n/4 elements of A as zeros. So there is another write dependency between operation 3 and operation 5. Likewise, we insert an edge from 4 to 6 to represent another write dependency. In the end, we copy values from array B to array A, Therefore, there's a read dependency between operation 5 and operation 7, and there is a write dependency between operation 6 and operation 7. After constructing the value flow graph, we annotate necessary information on the graph to assist analysis and optimization. First, we annotate call path at each GPU operation. For example, at operation 5, we annotate its call path from full to bar to set zeros and to CUDA launch kernel so that users can find out its related source code and perform optimization. We also addressed edge and vertex to reflect coarse-grained value patterns. We address edge width to reflect how many bytes have been written or read on each edge. We also addressed edge colors to reflect the redundancy ratio. Red colors often means significant redundancy ratio. We also change vertex size to reflect how many times a GPU operation has been called. We also address vertex colors to identify if these operations involve the same values. So in this example, these nodes are colored as blue since they all involve read or write up to zeros.